warahmatullahi wabarakatuh. In this section, we will discuss about subsequence and the Bolzano-Weierstrass theorem. Let me introduce our members of Group 9. First, there are Siti Latifatul Humaira, Muhammad Abdul Mujib, and Riza Fahira Valinia. Definition: let x equals xn be a sequence of real numbers, and let n1 less than n2 less than blah 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 less than nk less than blah 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 be a strictly increasing sequence of natural numbers. Then the sequence xn equals x and k given by xn1, xn2, blah blah blah, x and k, blah 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 is called a subsequence of x. Then, for example, if x equals 1 per 1, 1 per 2, 1 per 3, blah blah blah, then the selection of even indexed terms produces the subsequence xn equals 1 over 2, 1 over 4, 1 over 6, blah blah blah, 1 over 2k, blah blah blah, where n1 equals 2, n2 equals 4, blah blah blah, and k of equals 2k, blah blah blah. Other subsequence of x equals 1 over n are the following: 1 over 1, 1 over 3, 1 over 5, blah blah blah, 1 over 2k minus 1, blah blah blah, 1 over 2 factorial, 1 over 4 factorial, 1 over 6 factorial, blah blah blah, 1 over 2k factorial, blah blah blah. The following sequence are not subsequence of x equals 1 over n, 1 over 2, 1 over 1, 1 over 4, 1 over 3, 1 over 6, 1 over 5, blah blah blah, 1 over 1, 0, 1 over 3, 0, 1 over 5, 0, blah blah blah. A tail of sequence C 3.1.8 is a special type of sequence. In fact, the m tile corresponds to the sequence of indices. N1 equals m plus 1, n2 m plus 2, blah blah blah, and k equals m plus k, blah blah blah. But clearly, not every subsequence of a given sequence need be a tile of the sequence. Subsequences of convergent sequence also converge to the same limit, as we now show. Then, Theorem 3.4.2. If a sequence x equals xn of real numbers converge to real number x, then any subsequences x xn equals x and k of x also converge to x. Proof: let epsilon greater than 0 be given, and let k epsilon be such that if n greater than or equals k epsilon, then absolute value of xn minus x less than epsilon. Since n1 less than n2 less than blah 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 less than nk less than blah 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 is an increasing sequence of natural numbers, it is easily proved by induction that nk greater than or equals k. Hence, if k greater than or equals k epsilon, we also have nk greater than or equals k greater than or equals k epsilon, so that absolute value xn minus x less than epsilon. Therefore, the subsequences x and k also converge to x. QED. Next, for example, a lim p power n equals 0 if 0 less than p less than 1. The solution we have already seen in example 3.1.11b that if 0 less than b less than 1 and if xn definition b power n, then it follows from Bernoulli's inequality that lim xn equals 0. We can see the solution, and then we also follow from the monotone convergence theorem that the square is convergent. We can see we have x equals lim x to n equals lim x n power 2 equals x power 2. Therefore, we must have either x equals 0 or x equals 1, since the sequence xn is decreasing and bounded above by p less than 1, we deduct that x equals 0. For next example B, lim c power 1 over n equals 1 if c greater than 1. This limit has been obtained in example 3.1.11c for c greater than 0, using a rather ingenious argument. This solution we get, therefore we have z square equals z, hence it follows that either z equals 0 or z equals 1, since zn more than 1 for all n element n, we deduct that z equals 1. We leave it as an exercise to the reader to consider the case 0 less than c less than 1, QED. The following result is based on the careful negation of the definition of limit xn equals x. It leads to a convenient way to establish the divergence of a sequence. Next theorem, 3.4.2. If a sequence x equals xn of real numbers converges to a real number x, then any subsequence xn equals s and k of x also converge to x. Proof: let epsilon greater than 0 be given, and let k epsilon be such that if n greater than or equals k epsilon, then absolute value xn minus x less than epsilon. Since n1 less than n2 less than blah 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 less than nk less than blah 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 is an increasing sequence of natural numbers, it is easily proved by induction that nk more than or equals k. Hence, if k more than or equals k epsilon, we also have nk more than or equals k more than or equals k epsilon, so that absolute value of xn minus x less than epsilon. Therefore, the subsequence of x and k also converge to x. Let x equals xn be a sequence of real numbers. Then the following are equivalent. when the sequence x equal xn does not converge to x element R. 2. There exists an epsilon 0 greater than 0 such that for any k element n there exists nk element n such that nk greater than or equals k, and absolute value of xn minus x greater than or equals epsilon 0. 3. There exists an epsilon 0 more than 0, and a subsequence x accent equals xn of x such that absolute value x nk minus x greater than or equals epsilon 0 for all k element n. For the proof, part 1 implies part 2. If xn does not converge to x, then for some epsilon 0 greater than 0, it is impossible to find a natural number k such that for all n greater than or equals k, the terms xn satisfy absolute value xn minus x less than epsilon 0. That is, for each k element n, it is not true that for all n greater than or equals k, the inequality absolute value xn minus x epsilon less than epsilon 0 holds. In other words, for each k element n, there exists a natural number nx greater than or equals k, such that absolute value xn k minus x greater than or equals epsilon 0. Next, for part 2 implies part 3. Let epsilon 0 be as in part 2, and let n1 and element n be such that n1 greater than 1, and absolute value x n1 minus x greater than epsilon 0. Next, for part 3 implies part 1. Suppose x equals xn has a subsequences x accent equals x and k, satisfying the condition in part 3. So we prove it. QED. Since all subsequences of a convergent sequence must converge to the same limit, we have part 1 in the following result. Part 2 follows from the fact that a convergent sequence is bounded.
Okay, the next material is divergence criteria. If a sequence big X equals xn of real numbers has either of the following properties, then X is divergent. The properties are: first, X has two convergent subsequences x prime equals x and k, and x double primes equal x r k, whose limits are not equal. And the second property is X is unbounded. Okay. For example, the sequence x defined minus 1 power n is divergent. We can take subsequence x prime defined minus 1 power 2n equals 1, 1, 1 until infinity, and we know that minus 1 powered by even numbers, the result will be positive number, that is 1. So x prime converges to 1. And then the subsequences x double prime defined minus 1 power 2n minus 1 equals to minus 1, minus 1, minus 1 until infinity. We know that minus 1 If powered by odd numbers, then the result will be negative numbers, that is minus 1. So x double prime converges to minus 1. Therefore, based on the theorem 3.4.5 at point I, let's say if the limit of two converges subsequences x prime and x double primes are not equals, then x is divergent. We know in this case is the limit of subsequence x prime and subsequence x double primes are not equal. That is 1 clearly not equals to minus 1. So we can conclude that x is divergent. The existence of monotone subsequences. While not every sequence is a monotone sequence, we will now show that every sequence has a monotone subsequence. We have the theorem of monotone subsequence that say if big X equals to xn is a sequence of real numbers, then there is a subsequence of x that is monotone. Proof of monotone subsequence theorem. For the purpose of this proof, we will say that the m term xm is a peak if xm greater than xn for all n such that n greater than m. That is, xm is never exceeded by any term that follows it in the sequence. Note that in a decreasing sequence, every term is a peak, while in an increasing sequence, no term is a peak. We will consider two cases depending on whether x has infinitely many peaks or finitely many peaks. In the case 1, x has infinitely many peaks. In this case, we list the peaks by increasing subscripts xm1, xm2, blah 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 until xmk, blah 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 until infinitely many peaks. Then we have xm1 greater than or equals to xm2 greater than or equals to blah 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 until xmk greater than or equals to blah 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 until infinitely many peaks. Therefore, the subsequence xmk of peaks is a decreasing subsequence of x. In the case 2, x has a finite number, possibly 0, of peaks. Let these peaks be listed by increasing subscripts xm1, xm2, blah 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 until xmr. Let s1 defined as mr plus 1 be the first index beyond the last peak. Since xs1 is not a peak, there exists s2 greater than s1 such that xs1 less than xs2. Since xs2 is not a peak, there exists s3 greater than s2 such that xs2 less than xs3. Continuing in this way, we obtain an increasing subsequence xsk of x. That's proof. The next is the Bolzano-Weierstrass theorem. We will now use the monotone subsequence theorem to prove the Bolzano-Weierstrass theorem, which states that every bounded sequence has a convergent subsequence. Because of the importance of this theorem, we will also give a second proof of it based on the nested interval property. We have the Bolzano-Weierstrass theorem that says a bounded sequence of real numbers has a convergent subsequence. The proof of the Bolzano-Weierstrass theorem. First proof, it follows from the monotone subsequence theorem that if big X equals to xn is a bounded sequence, then it has a subsequence x prime equals to xnk that is monotone. Since this subsequence is also bounded, It follows from the monotone convergence theorem 3.3.2 that the subsequence is convergent. Then the second proof, since the set of values xn such that n element of natural number is bounded, this set is contained in any interval I1 defined closed interval AB. We take n1 equals to 1. We now bisect I1 into two equal subintervals I1 prime and I1 double prime and divide the set of indices n element of natural number such that n greater than 1 into two parts. A1 define the set of n element of natural number such that n greater than n1, xn element of I1 primes and B1 equals the set of n element natural number such that n greater than n1, xn element of I1 double primes. If A1 is infinite, we take I2 define I and let n2 be the smallest natural number in A1. If A1 is a finite set, then B must be infinite, and we take I2 define I1 double prime and let n2 be the smallest natural number in B1. We now bisect E2 into two equal subintervals I2 prime and I2 double prime and divide the set n element of natural number such that n greater than n2 into two parts. There are A2 and B2. A2 equals the set of n element of natural number such that n greater than n2, xn element of I2 prime and B2 defined as the set of n element of natural number such that n greater than n2, xn element of I2 double prime. If A2 is infinite, we take I3, define I2 prime and let n3 be the smallest natural number in A2. If A2 is a finite set, then B2 must be infinite, and we take I3 defined as I2 double prime and let n3 be the smallest natural number in B3. We continue in this way to obtain a sequence of nested intervals I1 subset of I2 subset of blah 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 until subset of IK subset until infinity and a subsequence x and k of x such that x and k element of IK for k element of natural numbers. Since the length of IK is equal to
Next, Theorem 3.4.9. Let big X equal xn be a bounded sequence of real numbers, and let X element R have the property that every convergent subsequence of X converges to small x. Then the sequence big X converges to small x. Proof. Suppose m greater than 0 is a bound for the sequence big X, so that the absolute value of xn less than or equals m for all n element natural numbers. If big X doesn't converge to small x, then Theorem 3.4.4 implies that there exists epsilon 0 greater than 0 and subsequence big X prime equal xnk of big X such that the absolute value of xnk minus x greater than or equals epsilon 0 for all k element natural number. Since big X prime is a subsequence of big X, the number m is also a bound for big X prime. Hence, the Bolzano-Weierstrass theorem implies that X prime has a convergent subsequence X double prime. Since X double prime is also a subsequence of big X, it converges to small x by hypothesis. Thus, its terms ultimately belong to the epsilon zero neighborhood of small x, contradicting with 1. Definition 3.4.10. Let big X equals xn be a bounded sequence of real numbers. A. The limit superior of xn is the infimum of the set big V of small v element R such that v less than xn for at most a finite number of n element natural number. It's denoted by, you can see the symbol, and B. The limit inferior of xn is the supremum of the set of W element R such that xm less than W for at most a finite number of m element natural number. It's denoted by, you can see on the PPT. Theorem 3.4.11. If xn is a bounded sequence of real numbers, then the following statements for a real number x star are equivalent. A. X star equals limit supremum xn. B. If epsilon greater than 0, there are at most a finite number of n element natural number such that x star plus epsilon less than xn. But an infinite number of n element natural number such that x star minus epsilon less than xn. C. If um equals supremum xn where n greater than or equals m, then x star equals infimum where m element natural numbers equals limit D. If S is the set of subsequential limits of xn, then x star equals supremum S. Proof. A implies B. If epsilon greater than 0, then the fact that x star is an infimum implies that there exists a small v in big V such that v greater than or equals x star and v less than x star plus epsilon. Therefore, x star also belongs to V. So, there can be at most a finite number of n element natural numbers such that x star plus epsilon less than xn. In another hand, x star minus epsilon is not in big V, so there are an infinite number of n element natural numbers such that x star minus epsilon less than xn. B implies C. If B holds given epsilon greater than 0, then for all sufficiently large m, we have less than x plus epsilon. Therefore, infimum where m element natural numbers less than or equals x star plus epsilon. Also, since there are an infinite number of n element natural numbers such that x star minus epsilon less than xn, then x star at minus epsilon less than for all m element natural numbers, and hence x star minus epsilon less than or equals infimum where m element natural numbers. Since epsilon greater than 0 is arbitrary, we conclude that x star equals infimum where m element natural numbers. Moreover, since the sequence is monotone decreasing, we have that infimum equals in limit C implies B. Suppose that big X prime equals xn k is a convergent subsequence of big X equals xn. Since nk greater than or equals k, we have that xnk less than or equals uk, and hence limits big X prime less than or equals limit uk L equals x star. Conversely, there exists n1 such that u1 minus 1 less than or equals n1 less than or equals u1. Inductively, choose nk plus 1 greater than nk such that nk plus 1 greater than uk minus 1 over k plus 1 and nk plus 1 less than or equals uk. Since limit uk equals x star, it follows that x star equals limit x and k, and hence x star element S. D implies A. Let W equals supremum S if epsilon greater than 0 is given, then there are at most finite many n with W plus epsilon less than xn. Therefore, W plus epsilon belongs to big V and limit supremum xn less than or equals W plus epsilon. In another hand, there exists a subsequence of xn converging to some number larger than W minus epsilon, so that W plus epsilon is not in big V, and hence W minus epsilon less than or equals limit supremum xn. Since epsilon greater than 0 is arbitrary, we conclude that W equals supremum xn. Theorem 3.4.12. A bounded sequence xn is convergent if and only if limit supremum xn equals limit infimum xn. You can prove as an exercise.